Welcome, Calculus 3 students. We are looking at double integrals and finding volumes. Today it is an extension of what we did last time. In this particular section we are looking at functions that are continuous, such as this 2x squared y. And what we're doing is we are going to bound this function by two functions. So we're cutting this function on the top and on the bottom. Now if we were to find the area of this, we would need to do this in terms of the y and x, and we're going to do the same thing that we did before. I'm going to integrate with respect to y first. It's going to make things easier because these limits of integration are in terms of x. And I'm not really sure what this is doing, why they wrote a -1 up here, but this should be a 2 because x varies between 2 and -2, so that's the integral that I'm going to solve here. So I'm going to write that down and then start the solution of this. Alright, let's take a moment and look at what I've done so far. I wrote down my integrals. I integrated with respect to y, and now what I've done is plugged in those limits of integration. So I'm going to simplify and then I will integrate with respect to x. Pretty messy kind of problem here. After integrating and a bunch of messy stuff, you get that volume is 663.2. In our next example, we're going to be looking at the function 2 plus 1 over y, which is this yellow, and it's an elevation type of plane, and we are cutting this by these boundaries, y equal x, y equal 8 minus x, and y equal 1. So here we have this sitting here in this bottom graph. Now I've got to figure out my limits of integration. And if I tried to integrate this with respect to x, note that I would have two separate integrals that I'm going to have to deal with and change those limits of integration. However, if I integrate with respect to y first, I can have this being my top function and this being my bottom function. So you will notice that is what they did when they wrote out their volume formula for this particular solid. And in this way you would integrate with respect to x first, and then you would integrate with respect to y. So we are going to do that. Alright, and then doing that computation on that integral, this is what I get. I do want you to notice though, when I integrate with respect to y, y is going to vary from 4 to 1, and so that's what those limits of integration are. I'm not really sure where this thing came from, so just note that that is a 4. I'm not really sure why they wrote that there. Anyway, alright, on to the next one. For our next example, we are given a z function that has this triangular shape, and what we're going to do is cut it in a way along that makes a pyramid, is basically what we're going to do. So I've got to figure out how it is that I'm going to integrate this, and I can integrate this with respect to y or x first. If I integrate with respect to y first up, that would mean that my integral would need, the top function would need to be my what this line is in terms of x. So that would be this c over b minus ax over b, and then the bottom one's pretty nice because that's a 0. And then what I would have next is my z function, which is the c minus ax minus by, and these were limits with respect to y. For my dx, I figure out how it is that the top and bottom, what this would be, and this goes from c over a to 0, and this would be my setup for my integral. So I'll get that completed. So when I finish this up with a bunch of messy algebra on a separate sheet of paper, this is what I end up getting. Now sometimes you'll set up your integral and you're going to find that it is uncomfortable to integrate this thing with respect to x because I've got an x squared there, and I'm not sure which technique I might try, but I know it's not going to be substitution or integration by parts. I can't. So anyway, they've given me this setup, and let me just go ahead and draw out these limits of integration and look at and see what they look like. So I'm integrating with respect to x is what they have me doing first. So if I try that, if I write these out, I see that here's my top function, here's my bottom function, and let's try and rework this, maybe rewriting it. I'm still going to have this, but I'd like to rewrite it so that I have limits of integration of y first. So let's look at that. So if I look top to bottom, my limits of integration are going to be an x and then 0, and then seeing what my x values are ranging from, that's going to be square root of pi to 0. And now I'm going to try to do this integration because, oops, sine x, put that in there. So that's just going to end up being y sine squared x, which is really nice, integrated from x to 0. And then I'll see what I've got. Oops, I put my square in the wrong place. I'll fix that. Now this one I can integrate as, let's let u equal x squared. That means du is going to be 2x dx, and I'll integrate with one of our old techniques there. Alright, and there we have it. Our volume for this region is A1. Alright, we now have two functions now that we are going to put together to create a solid that we're going to find the volume of. And we'll need to find, because each of these continues on in all directions and this one continues on in this direction, I need to find this exact intersection point between these two, and I need to project that down onto this xy plane so that I can get my limits of integration. How I'll do that is I'll just see where these two functions are equal. So I need to say x squared plus y squared equals, and I'll get that. So I see that they intersect in a circle of radius 2. Okay, so let's see what I have here for you. I've noted that the top function is 8 minus x squared minus y squared, and here's the bottom function. So it's going to be my top function minus my bottom function. I can choose to do this in quadrant 1 so that I can integrate from 0 to 2 here. As far as integrating with respect to x or y, this is a very symmetric type setup. So what we'll do is we'll just say that I'm going to say I'm doing it in one quadrant, so I'll say it's 4 times that, and I'll just integrate it with respect to y first and then x. So that means I need to write this in terms of x, and I'll just rewrite that, so that will be square root of 4 minus x squared, and this other limit of integration would be my 0. Alright, and I just need to integrate that and then I'll find the volume of this beautiful solid. And after quite a bit of manipulation and some trig substitution, you get 16 pi as your volume of that solid. In this last example, we are going to find the area of a region R. They don't tell you that we're looking at the area of a plane region, which means f of x, y equals 1. It's going to make it really nice, but that is what they are having us look at here. And their main point of this is that we've got this plane region and it's bounded by several different curves here that I can't break up nicely. Notice if I try to integrate with respect to x first, I've got an issue when it comes right this way because I have the same function top and bottom. I guess I could, I can't really double things. So what we're going to do is we're going to integrate with respect to y, and we are going to break it into two separate double integrals. So for my first, let's do volume is, for my first double integral, since I'm integrating with respect to y first, the top function is 4x plus 12. The bottom function is just x squared, and that is a 1 dy dx. Let's get my limits of integration for x. That goes from 0 to negative 2. Add with that double integral, and then a 1 dy dx. Let's get my limits of integration. The top function here is negative x plus 12. Bottom function is x squared, and the x values range from 3 to 0. And then I just integrate. Alright, and this would be my total on that volume for my plane region. Let me go ahead and restate that area of that plane region.